Welcome, everyone. Thanks for joining us and thanks for being part of our community. My name is Jason Cohen and I'll be your host for today. I'm also joined by my co-hosts, Valen Kolika, Ryan Heffernan, and Ashley Martin. A few reminders before we start. If you have issues viewing the stream at any time during the presentation and are using the web browser version of Teams, please refresh your browser. If you are using the desktop app of Teams, please exit and rejoin. Please note that this webinar is being recorded and will be shared publicly. We will post the recordings on our community at aka.ms/securitywebinars. Closed captions in several languages are available during the live broadcast. You can enable them by clicking on the CC button located at the lower right corner of your screen. Feel free to ask questions at any time by typing them in the live event Q&A window by clicking on the Ask a Question button. Be aware that any questions you post will be publicly visible. However, if you prefer, you can post your question anonymously by checking the box right below where you enter it. We often get many questions on these webinars and we will do our best to respond to all of them in real time. In the event if the answer was not provided or if you may have additional questions post this event, please don't hesitate to raise them on our Security Compliance and Identity Forum at aka.ms/SCI community or reach out at ATML@microsoft.com. We love to hear your feedback on how we can improve these webinars. You can do so at aka.ms/securityWebinarFeedback. And by the way, all the links that I'm announcing will be shared with you on the chat or the live event Q&A window shortly. I would also like to invite you to join our public community by visiting aka.ms/securitycommunity. That's the best way to ensure you don't miss any future webinars or major announcements. On our community, you can speak directly to our engineering teams that create our security products. You'll be able to influence our product designs and get early access to changes by doing things like participating in private previews at aka.ms/PRSecCom. Request features, give feedback, and reviewing our product roadmaps, register for events, or join webinars like this. We believe that the best way to improve our products is by removing any barriers between you and the people that create them. So we hope you'll join us. In today's session, Raja Dheekonda and Will Pearce will take us through cybersecurity fundamentals, hacking AI with Counterfit. Raja and Will are both software engineers with the Adversarial Trustworthy Machine Learning team. And without further ado, I'll turn it over to them. Raja, Will, the floor is yours.
Excellent. Hello, good morning. Welcome to the Cybersecurity Fundamentals webinar. By now, you might have heard about the terms artificial intelligence and machine learning technologies that's being used almost every organization in the planet. However, there's still an emerging need for the organizations to manage their risks associated with their AI systems before actual threat happens. Today, I'm going to show you that risks in AI systems are real using this tool called Microsoft Counterfit. By end of this presentation, you will learn how to assess risks in your AI systems using this tool called Microsoft Counterfit. My name is Raja Dheekonda. I'm a software engineer. I have been joined by my colleague Will Pearce, who is an AI team lead. We are from Azure Trustworthy Machine Learning team in Microsoft, where our core mission is to empower every organization in the planet to manage their risks in their AI systems. So why should you care about securing your AI systems? Well, as you all know, artificial intelligence and machine learning technologies are being used almost every sector. For instance, in healthcare, to predict the diagnosis of the patient by assessing the patient's medical condition data. Or in financial sector, to predict whether a particular transaction is fraudulent or benign using transaction summary of the users. Or even in retail sector, to recommend the items to the users based upon the user's usage activity data. So as you all see that AI and machine learning technologies are being used almost everywhere, but still there exists a risk associated with their AI systems that impacts directly or indirectly to your business. So AI risk is business risk. So what is the right trade-off? Do you want to build your AI systems that is performance efficient, that maximizes accuracy, predicts well in the generalization settings? Or do you want to build your AI systems that's robust enough for adversarial attacks? But it comes with a cost. With that, I'm going to hand over to my colleague Will Pearce, and let's get started.
Thank you, Raja. Next slide. So I'm going to tell you a story about before I was the red team, a machine learning red teamer. I come from the red team space, the traditional red team space, and we had issues getting phishing emails past a particular spam filter. And it was a very good spam filter, and a lot of similar teams had issues with it. And one day we noticed that this filter in its headers was leaking these scores. And we did some research and we found out that this particular product uses machine learning to score phishing emails to see whether or not it should let it through or not. So we devised a way, so we did some research and we devised a way to steal the machine learning model and reverse that model in a very brutish type of way. And then we were able to create emails that bypassed the spam filter. And that resulted in CVE 2019-20634, which is the one you see below. And it's the first CVE for a machine learning system. But in reality, there are a lot of attacks that already exist against machine learning systems. They just exist in a research space or an academic space rather than an industry space. Next slide. Do I have control?
I think Raja has control.
Yeah, I'm like next slide.
Great, thank you. And so what we're looking at is an explosion of adversarial machine learning research, both in academia and in industry. So these are all headlines that I've collected from the news over the past 2 years. We have all kinds of things. We have personal voice assistants not recognizing particular voices. We have large language models memorizing phone numbers from public information. Just because information is public or data is public doesn't mean it should be public, and certainly doesn't mean it should have been trained in a machine learning model. All the way to safety, to with cars, or regular security vulnerabilities like deserialization in pickle files or other serialized formats. Or we have the classic security bypass for machine learning systems. And I'm sure most of you will be familiar with the stories in the news that we hear. And while it seems futuristic, a lot of these things seem futuristic, and a lot of the titles are hyped, maybe because they are in the media. The reality is that there is some truth to these, and there is some impact to these, even if we're not necessarily familiar with what that impact is, or we don't have the logging to be able to detect these things at a large scale. So the state of machine learning security is such that the awareness of the risk is low. The education on both sides, both the security side and the machine learning side, is low. So security folks don't know the ins and outs of machine learning, and machine learning folks don't know the ins and outs of security. But what that means is our security posture is really close to zero. And there's a lot of low-hanging fruit at the moment for machine learning systems, which is arguably why somebody like me from the security space can, I wouldn't say easily, but relatively easily, relative to getting a PhD, let's say, come into the space and start stealing models or start having an impact on the security of these models. And there are a lot of people like me who are doing research and looking for new areas that they can breach systems and compromise data through adversarial tactics. And Microsoft did a study, a survey, and they found that 25 out of 28 companies don't know how to secure their machine learning systems. And it's really not a surprise, because there's not a ton of guidance out there. We don't have the risk assessments that security, we don't have databases full of CVEs that we can test. We don't really have tools or really a large understanding about outside of the machine learning engineer space. Security doesn't have an understanding of how the machine learning workflow is supposed to go and where an attacker can inject themselves into the process. But really, for our thing, machine learning does represent a new attack surface. But when we talk about technical security maturity, typically we have a very good idea of what we need, right? We need an asset inventory. We need a basic risk assessment to go and check some boxes and make sure that we're good with our basic. We have our foundational security thing, and this is where regular auditing comes in. And so if you think GRC or ISO 27001, this is machine learning is in need of some sort of auditing framework or risk framework, some way we can start to communicate about the risks. Once we have our auditing in place, we can start vulnerability scanning, or we can do these simultaneously. But once that's in place, we can start baselining our models, and we can start vulnerability scanning. We take all the publicly known algorithms, and we're just scanning anything and everything for weaknesses. And it's really just about getting coverage of assets and learning what's in your environment and how it reacts to adversarial testing. Then next piece, we have technical testing, and this is really actively exploiting those found assets or those assets in your inventory for an impact analysis. So it's like, if there is an actual adversary, what impact could they possibly have? In a lot of spaces, this is just to confirm vulnerabilities, but you really want to attack assets with coverage in mind. So you're trying to get a broad stroke, not necessarily a deep dive, but just to get start going through the process of securing. And then, of course, finally, we have red teaming, and this is a traditional practice that comes out of the military, where it's really just thinking like an adversary. So you take on a persona of an adversary, and you're testing a specific scenario or use case. So you're looking for worst case scenarios. So if a large language model was trained on customer data, let's say, and it's known that large language models tend to memorize their training data. So can you, as an adversary, pull out customer data from that large language model? But the attacks against ML are, at a high level, are extraction, evasion, inversion, inference, and poisoning. And these can happen in a few different places, but on the left you have a data collection. This is kind of the machine learning dev pipeline, and it happens in a circular fashion, in that new data comes into the system through inference, and then new models get deployed. So it's kind of a model is a moving target in a lot of ways. Especially in more of the more dynamic environments. Although in some environments, it could be rather static because you want a very specific outcome. But in some environments, it could be more dynamic. But we also, so there are two types of attacks. Basically, we have a train time attack, and these attacks happen before the model is deployed. So you can think of this perhaps like a supply chain attack, where we have the recent SolarWinds, where some code is poisoned, or a piece of software is backdoored. You can think of this like that, where some data is backdoored, or hyperparameters are messed with, or the labels are changed, and that has cascading effects through the model training and then the deployment. And really, here we have poisoning attacks. And then the next one, we have inference time attacks. And these are attacks post-deployment, where the adversary can submit inputs and receive outputs, and try and triangulate information, or there are a lot of public algorithms that can be used to steal a model or bypass a model. And here we have extraction, evasion, inversion, and inference. Extraction is, we steal a model, we're pulling some internal information out, or a functional equivalent. Evasion is we're just causing a misclassification, and this could be malicious or non-malicious. Inversion, we're recreating, or we're pulling out training data from the model. And then inference is we're getting a model to confirm whether or not a model was trained on a particular data point by exploiting confidence values and all output. But now Raja is going to show you a demo of Counterfit and show you some real-world attacks that are based, well, they're based on real-world attacks that we've done here, and I'll give it over to Raja.
Thank you so much, Will. I really appreciate for going over classification of attacks across different stages of the machine learning development lifecycle. Now I'm going to talk about some of the real world attacks that are possible on AI systems. Before dive deep into like some of the attacking algorithms that are possible on the machine learning systems, especially on the evasion technique, which Will has shown. So I'd like to emphasize two important stages of the machine learning development lifecycle called training and inference. On the top, you would see the training phase where you get model input data that gets represented in features. Features are the measurable property. For instance, you can think as age or a total dollar amount spent in a particular transaction, or if it is an image, a feature is a pixel. So that gets so in this case, I'm taking images data, like set of images that gets represented in pixels as the features, and that get passed into the machine learning training algorithm. And then we compute the gradients and class labels. Then we compute the error. So error is the difference between the true class label and the predicted class label, and we back propagate the error all the way to the initial layer. In this case, it's deep neural network that I'm showing here. So then the goal of the training is to minimize the error and maximize the accuracy that works well in the generalization setting. So once you have the best model and best parameters, best hyperparameters that works well in the generalization setting, then you deploy that model into the production, and that is ready for inferencing. And then you get the input request. So in this case, we are in the bottom, we can see that's the inference stage where you get image as an input, and the model will predict that it has a lion in this case. So what's really happening in the training stage? So in the training stage, we are the training algorithms compute this decision boundary. So what is a decision boundary? Decision boundary is a surface that divides the data points belongs to different class labels. For instance, as you can see in the middle of this picture, we have two image labels, koalas and ducks. So once you pass that to the model will differentiate between these two different sets of class labels by using the decision boundary, which is a linear line. It separates these two different class labels. So once you have that, in reality, you will not have this linear decision boundary, quadratic or different shapes that you will have the decision boundaries. So once you have this trained model, then we pass our model input on the left-hand side, duck. Then the model will predict that as duck with some confidence. So decision boundaries plays a huge key role in the attacking algorithms, and one of the attacking algorithm is called boundary attack. Boundary attack is a black box technique where the attacking algorithm doesn't need to require any details about the model architecture, model parameters, hyperparameters, or what was the algorithm that's being used for the model training, or any of the architecture. All it requires is, it's a black box technique. All it requires is for this attacking algorithm, class labels and respective probabilities or confidence that model endpoint predicts. So once you have this like trained model, then we pass, for example, here like we are passing model input duck to the trained model, and the model is predicting it as duck with confidence 0.97. So what is the goal of the boundary attack? So the goal of the boundary attack is to perturb the input pixels such that the model will misclassify the input class label after certain number of queries and subsequent input feature changes. So let's take in this example. So initially, as an attacker observes the model input, and the probability was 0.97 that it was the original class label was a duck. But once we pass this image to the attacking algorithm, in this case like boundary attack, then the attacking algorithm tries to change the input pixels such that the model will predict as in this case like it's predicting as duck with confidence 0.75. As we can see here, the confidence is getting reduced from 0.97 to 0.75 after certain number of queries and perturbations that's happened to the input image. After certain number of queries and subsequent input feature changes, now the original image, which was duck, now the model is predicting as koala. We completely fooled the system, even though the original class label was it was duck. Now it is predicting as a koala with confidence 0.65. This is a probability. And you can do all this by yourself starting today. On May 3rd, 2021, we released a free and open source tool called Microsoft Counterfit that enables you to do two things. You can probe your AI systems for vulnerabilities, and you can log your results for that probing. Counterfit is an open source tool. Microsoft Counterfit is an open source tool that assesses the security of your machine learning systems for vulnerabilities. It is mainly built on two most popular open source frameworks called Adversarial Robustness Toolkit and Text Attack. And I'm going to show our first demo. Here, let's take a deep dive into our demos, which I'm going to show. As a security analyst, I would like to assess the security of satellite image classification system. Satellite image classification system is built on two classes, aeroplane and the stadium. So the goal is given an image, we would like to predict whether a particular image is aeroplane and or stadium. And we would like to assess whether the security of this satellite image classification system. Some of the real world scenarios for satellite image classification system is like geo environmental or defense sector, where you can use the spatial images and you can predict whether a particular image is respective to a particular class label. Our first step number one, as an attacker, I pass the input image to the model endpoint. This is like already deployed model. Pass input to the model endpoint, and the model is predicting that it has aeroplane with 96% confidence. Just attack as an attacker, like just take. This is our step number one, just observing the class labels and the respective probabilities in the system. In the next step, then we pass it to the one of the attacking algorithm that's part of the counterfeit. Then the model is predicting as a stadium with 92% confidence after certain number of perturbations to the sample image and subsequent input updates, like tiny feature changes that we are gonna make as an attacking algorithm. It's gonna make to the input image. With that, let's dive deep into our demo. We'll see this in the live demo environment. So once you have Counterfit installed and up and running in the Jupyter Hub, you can see like something like this. On the top, you can see the terminal. In the bottom, I have scripts that I'm going to show for the satellite image classification system, the security of the satellite image classification system, and see whether we can fool the system, satellite image classification system, by taking the sample input as aeroplane and make it predict like stadium, make the model predict like a stadium, whether we can fool the system by passing it to some attacking algorithm as part of the counterfeit. So currently Counterfeit supports 18 attacks. That's part of the attacking frameworks, and 4 targets. These are the machine learning models that is deployed and it's pre-packaged with Counterfeit. Once you install and Counterfeit is up and running, you have 4 targets, and you can see all the targets using this command called list targets. And as you can see here, you have 4 targets, satellite images, and it's the model data type is image, and the input shape is 256 256 because these are colored images, like you have RGB channels. And the location, it's a local location. If you deploy Counterfeit, if you install in our local, the models will be installed in our local, or you can deploy into some REST endpoint, and you can point that REST endpoint to this location. Counterfeit will take care of the rest of the things. And tutorial, this is the MNIST data set, which is of image data type, and input shape is 12828. And movie reviews, which is a NLP based application to see the review, to predict the sentiment of the review, whether it is positive sentiment or negative sentiment. And the credit fraud transaction, which our second demo is credit fraud, which is of type NumPy, which is a Python data structure that can our first demo is we would like to interact with the satellite images using this command called interact. So we are loading the particular target of satellite images. The model is loaded successfully. If you would like to see some information about this model, so the command is called show info. It tells you a little bit information about the model. The model name is satellite images, and the model data type is image. And model endpoint, currently it is deployed to local, and the shape, model input shape, and the model output classes, aeroplane and stadium, because we trained the model on two class labels, aeroplane and stadium, and some docs are related to it, image recognition model that leverages, it's built on ResNet 50 pre-trained model. Then I would like to use like some of the attacks that is related to image type, and we can see what all are the attacks that are possible on this image data type. In order to do that, we can use this command called list frameworks. List frameworks is wrapped two popular open source frameworks called Adversarial Robustness Toolkit, refers to ART, and it got 7 attacks, and text attack, which has got 11 attacks. Then you can use load the framework ART, because ART supports both image data type and NumPy data type, tabular data types. Then you can see all the attacks under the ART framework. It has got 7 attacks. Out of 7 attacks, 3 attacks supports both image and NumPy data type, such as zoo, hop, skip, jump, a boundary attack. This supports both image data type and NumPy data type. So for this exercise, I will go ahead and use my favorite attacking algorithm called hop, skip, jump. So using this command called use hop, skip, jump, then the particular attacking algorithm is loaded into the counterfeit successfully. So our next operation, if you want to see more information about this algorithm, attacking algorithm, there is a command called show info, the same that we executed for the target. Here you can see the information related to the attacking algorithm. It is hop, skip, jump, and attacking type is evasion, and it falls under black box, which means the attacking algorithm doesn't need to worry about, doesn't require any details about the model architecture, hyperparameters, or parameters, or what framework that the model is built on. So all it needs is just class label and respective probabilities, how confident that the predicted image or predicted feature is related to a particular feature class label. Then we have tags. Then it falls under ART framework. This attacking hop, skip, jump falls under ART framework. And a little information about this algorithm. And if you'd like to know more about this hop, skip, jump attacking algorithm, this is a research paper. Need machine learning mathematics underneath it. It's pretty cool. I would highly encourage if you'd like to go and watch, go and read this paper. So for this exercise, I'm setting the attacking parameters using this command called set. Set init size equals 50 and max iter 20 and max eval equals 500. I'm setting like some of the attacking parameters in this context. So here our goal is by taking the sample input image of aeroplane and pass it to the attacking algorithm and see whether we can able to fool the model by sending like aeroplane image and make it look like stadium. So in order to do that, you can use this command predict. It predicts. I'm taking the sample index 0, this sample input image of satellite image, and as you can see here, the model is predicting that as aeroplane with probability 0.96. So then you can run the attack. So we are passing that sample input image to the attacking algorithm called hop skip jump in this case. Then it is attacking on the particular image and on the particular model. And after certain number of queries and we successfully fooled the system. As you can see here in the output, one by one succeeded, and we have taken the sample index input as aeroplane image with 0.96 probability, that is aeroplane image. Then after running some attack, a hop skip jump, then the model is predicting it as stadium with 0.92 probability. It's not only we flip the label, but it has taken like almost, if you see the difference between the original image and the modified image, the final image, it is 0.0000 percentage, which is hard to view the differences between two images, the original label and the original image and the final modified image. But the model is thinking like completely different. Instead of like aeroplane, it is predicting as stadium. And it has done in like 7.4 seconds. So the attacking algorithm, as we have seen, it just took like 7.4 seconds. And in 54 queries in the sense that many number of iterations or perturbations that's made on the input feature set. So you can see the final label using this command called predict-r. This will give you the predicted result. Like once we attack on the particular sample input, then we can see the predicted probability using this command called predict-r. So this is the attack ID that we hop skip jump, and the sample, this is the sample that it generated after the attacking. Now the model is thinking it as stadium with 0.92 probability, that is stadium. So we can see the outputs here in the once we run the attack, we can see the output images under this folder called satellite images. Here we have this is the initial image that we passed to the system, and the model was predicted that it has stadium, that it has aeroplane with 0.96 probability that it has aeroplane. So after passing this sample image to the attacking algorithm, now you can see on the right hand side, that's the adversarial image, or after running the attack on the left hand side, that was the original image. The model was predicting aeroplane with 0.96 probability. On the right hand side, after passing it to the attacking algorithm, the model was predicting as a stadium, even though the original label was aeroplane with 0.96. How cool it is using this attacking algorithm, like completely we fool the system. So definitely our satellite image classification system is not secure enough. And see here, so what we have done in the in our demo number 1, we have taken the initial like sample image, which is of class label aeroplane with 96% confidence that we are saying that is aeroplane image. That's great. But after we pass that to the attacking algorithm, what we have seen using hop skip jump, now the model is thinking as stadium. And as a human, I can't differentiate between these two images, even though it looks like aeroplane. On the right hand side, if you see hardly very few pixels that we perturbed to the input image, but still we successfully fooled the system, evaded the classifier by generating this adversarial example. And this is bad, like we completely fooled the system. And not only we are completely fooled the system, but also with high confidence. As you can see here, the original class label was 96% that we are that model is predicting that it is aeroplane. But after running with some attacking algorithm, then the model is predicting with 92% confidence that it is stadium. Not only like flip the label, but with high confidence. In our second demo, as a security analyst, I would like to assess the security of my credit card fraudulent system. This credit card fraudulent system, where we use every day to day in our lives, whether a particular transaction is fraudulent or benign, that's the model that we trained on. for this exercise, again, like this, our step number 1, to observe the environment by passing some transaction to the model endpoint. This is a credit card fraud model detection. Then initially we observe that it has fraudulent transaction by using like some summary of the features of the particular transaction, such as total dollar spent and the date and time and the user details. We pass that feature set to the model endpoint, and it is predicting as a fraudulent transaction. Then we pass that to some attacking algorithm, like in the previous case we used hop, skip, jump. We can use the same attacking algorithm because it supports both NumPy data structure as well as image data type. We pass it to some attacking algorithm, and let's say after certain number of queries and respective subsequent input feature changes, now the model is predicting as benign transaction. Even though the original transaction was fraudulent, now it is predicting as a benign transaction. With that, let's take a look into our demo number 2. So I'm here in like demo number 2. So you can refresh the environment using this command called back. So back will refresh. We are exiting the satellite images, that the first model that we assess the security. Definitely it's not secure. So for the second demo, I would like to see all the targets that are in the counterfeit using this command called list targets, the same command. And as you can see here, we have satellite images, tutorial, movie reviews, credit fraud model. So for this demo number 2, I will go ahead and use credit fraud because we would like to assess the security of the credit fraud model detection and how secure it is by passing the fraudulent transaction, and after certain number of queries or passing it to some attacking algorithm, and see whether we can successfully fool the system by flipping fraudulent transaction to the benign transaction. That is our exercise. Then I can see all the frameworks, and as art supports both NumPy data type and image data type, so I will go ahead and use load the art framework. So framework loaded successfully. Then we can see all the attacks underneath the art framework using the command called list attacks. So as you can see here, we have out of 7 attacks, 3 attacks supports both image data type and NumPy data type. Like for example, zoo refers to zero order optimization, and hop, skip, jump, and boundary attack, which supports both image and NumPy data type. So here for this exercise, I will go ahead and use, there is a new command called scan. In the previous demo, we have seen the usage of run. So run takes the default parameters, attacking parameters, whatever the parameters that exist in the code, it takes the default parameters. But scan, it observes the random parameters for the attacking algorithm. It sets the random parameters to the attacking algorithm. So as a user, you don't need to come up with like different attacking parameters. So with this parameter -n, 3 iterations of the particular attack that we are gonna run, and you can also log the intermediate results. We have to load the target. So here we are not interacting with the target, so we can use that with this command called interact credit fraud. That is our model. So then you can run this scan command. So what it is doing, like 3 iterations of all the attacks that is supported for the NumPy data type, and after after some time, then we can see the result here. It supports 3 attacking algorithms for the NumPy data type, and hop, skip, jump is one among them. And out of total 3 runs, and 2 are successful. Successful in the sense we successfully fool the system by flipping either fraudulent transaction to the benign transaction. And you can save the intermediate logging results using this command called save. Save will persist the all the intermediate logging, all the intermediate interactions that we have done to the model endpoint. And if you want to see like all the data under this JSON file, there is a command called tail -n 1000. We can provide this file name. It contains the model input, model output, and all the intermediate interactions. So as you can see here, we have timestamp at what time that we perform the attack, and model ID, and attacking name, and attacking ID, and respective inputs and outputs, and the labels, all the intermediate details that we can view here. So for this exercise, we would like to take the fraudulent transaction. We can predict, we can see the feature set using this command called predict-i zeroth sample index. And as you can see, this is the transaction that is fraudulent here with probability 1 that it is fraudulent. And then we would like to see scan the model by passing this sample input and see whether we can able to flip the label from fraudulent transaction to the benign transaction. I'm using the same command like scan because I don't know what are the parameters to set for this. So I'm using like scan for this demo. Then you can set the sample index because as we know, the sample index 0 corresponds to the fraudulent transaction here, which is a probability 1 that is fraudulent transaction. So I'm taking that fraudulent transaction by setting the sample index parameter. And then here I'm using the same attack called hop skip jump. As we know, hop skip jump supports both image data type and numpy data type. Then you can enable verbose. You can see like all the information, all the summaries, all the details related to this particular scan. As you can see here, a scan summary, we have this attacking name and total 3 runs because we provided the parameter -n 3 times because hop skip jump, we ran hop skip jump 3 times, and all the 3 times the scan attempts to provide attacking parameters in a random fashion. So we haven't set any of the, like for example, max iteration, max eval, some of the attacking parameters set automatically from the random distribution. And out of 3 runs, 3 were successful, which means we took the fraudulent transaction, and all 3 fraudulent transactions, it made it look like a benign transaction. That we can see here, the best parameters and the best scores. And these are the number of queries that it has taken. So from this, let's take the best score that we identified and run the attack again. So using hop skip jump. So I'm using hop skip jump, and I know these are the best parameters. So you can set the best parameters as sample index 0, targeted 1, target class 0, and init evaluation is 100, max eval is 500. And then we can run the attack on this sample. What we have done, we have taken the best parameters from the scan because scan sets the parameters in a random fashion. So we took those parameters and run the attack on the sample index 0. So the original class label was fraudulent with confidence 1, which means that 100% the model is predicting that it has fraudulent transaction. And after running the hop skip jump attack, then the model was predicting as benign with probability 1, which is like almost high confidence. And with less Euclidean distance. Euclidean distance is, you can think as a distance between original feature set and the final after running the attack, whatever the values that we see in the final feature set. It is very less, like hardly less than 0.005%. And it took 0.6 seconds, just like matter of milliseconds in the seconds, we completed this attack, and it has taken 21,000 queries. So we can see the predicted output using this command called predict-r. So this is the feature set that after running the attack, that attacking algorithm it's produced. So, but the model is predicting as benign. Benign means a legitimate transaction. And we can see the feature set of the original features. So in the bottom, you can see the original features that we passed to the model, and the model is predicting as fraudulent transaction. But after running the attacking algorithm, the model is predicting as a benign, a legitimate transaction. And here, as you observe here, like some of the fields, for example, like dollar amount hasn't changed, $239.93 and $239.93. Dollar amount hasn't changed, but like some other features, it was changed. Here you can see one feature, it is negative 1.34, and here it is saying like negative 1.33. It could be like some time of the day or a day or some other transaction summaries. We successfully fooled the system by passing a fraudulent transaction and using attacking algorithm, and it made it look like benign transaction. So definitely our credit card fraud detection model is not secure enough against this kind of attacks. So what we have done in the demo number 2, we have taken the fraudulent transaction with the dollar amount, $239 and time and some of the transaction history, and then used some attacking algorithm from the counterfeit. Then after some time, then the model is thinking that as benign transaction, legitimate transaction, even though the dollar amount and some of the fields aren't changed, and even if there is any perturbations changed a tiny bit, as we have seen, the Euclidean distance is very less between this original and modified feature set. As we can see, both our satellite image classification system and credit fraud detection both are not secured enough against this adversarial attacks. With that, I'm going to hand over to my colleague Will Pearce to conclude the rest of the presentation.
Thank you, Raja. This is always my favorite demo. So we like hop, skip, jump. It's a good one. Yeah. So in conclusion, these are obviously models we trained ourselves for the sake of a demo. But these are based in real ops that we've done, and real models that exist probably in a lot of organizations. So, obviously real, but the tools and techniques already exist to exploit these systems, even if Counterfit didn't exist. So Counterfit is just a wrapper, right? Like I come from a security background, not a machine learning background. I needed a way to scale, make it easy for myself, make it easy for us as a team to scale attacking machine learning. So it's really just a wrapper around these existing frameworks. And so even if Counterfit didn't exist and we weren't here, the tools and techniques already exist to exploit these systems. In terms of defending these systems, traditional security practices are important to secure these systems. So logging, access control, asset inventory, and things like that. And then really just sit down and think about how your system could be exploited. So, what are the possible outcomes? What's the worst possible outcome for a particular system? And then how might an adversary achieve that goal? And then, obviously, Counterfit is built to use. So go and try it on your models. Go and try it on the example models that we have there. It's really designed for people to go and experiment and learn about their models and go and find vulnerabilities and really wrestle with the problem with, like, what does it mean to secure a machine learning algorithm? And through sort of both the machine learning side and the security side, we'll come to some answer that we can start using in production. And then contribute, learn more on the wiki. We have some assessment guidance, we have some defensive guidance, then we have some more advanced use cases. So, if you're a red team and you want to start attacking models, we have some things where you can distribute traffic through proxies. And, if you're familiar with Cobalt Strike or Metasploit, you'll find the workflows similar. And with that, we just want to say thank you. And if you have any questions or comments, please email myself or Raja or this ATML, which is our entire team. And we are ready for questions.
Great. So it looks like we have two. First one is there a way to include attacks like this into the training process to calculate the susceptibility of the model to known attacks as a metric and minimize it?
Yes, yeah, you could absolutely do this pre-deployment or post-deployment. Counterfit is designed really to attack arbitrary endpoints. So I think one of the things we did was to create a black box classifier wrapper, and so it can really talk to any arbitrary endpoint you would like, so it kind of assumes a black box setting, like it assumes no information and then goes up from there. So if you want to use it in a training pipeline, you could certainly do that. It's built on the CMD2 library, so it has some neat scripting things that you could do if you wanted to automate it. It doesn't have an API, but it does have the ability to script attacks.
Great, thank you. And the next one is, how many scan iterations is usually enough to get results on practical models? 3 does not seem like much.
It will depend on the model and the algorithm used. So for example, hop, skip, jump is boundary attack 2.0. And so I think you'd always expect hop, skip, jump to require less iterations than boundary attack. But that's something I think that we don't have a lot of information about at the moment. So, what attacks work best against which models, and then what parameters, right? I think obviously the parameters are kind of make or break for the number of iterations, right? Like the demos that Raj used, we'd gone through this process and we had cherry picked parameters that would give us a fast result for the sake of demos. So it's really going to depend on the model, the algorithm you use, the input, any domain knowledge you have in the area. So, if you used to write malware, right, you're going to have an easier time bypassing the malware classifier. I don't know if Raja would have anything to say about that.
Yeah, I would like to add to Will. It's like depends upon the algorithm, or depends like how robust. If it's very hard to bypass the gradients or bypass the decision boundary, and even like after a certain number of queries, the attacking might be unsuccessful. So I think that's good, right? So in this context, so I think if more number of queries and the more Euclidean distance, so that is bad. So which means we are not, the attacking algorithm is failing. So in that case, the models are robust against this kind of. But you can increase some of the parameters like max evaluation, max iterations, and from there you can get a sense of what's happening in the attacking space and models.
Great, thank you so much. So I think that's the end of the questions that we had. Thank you, Raja and Will, for being our guests today and for an excellent presentation. And thank you to the rest of the team who helped answer questions. At the same time, I would like to remind the listeners that the best way to ensure you don't miss any future webinars or major announcements is to visit our landing page at aka.ms/securitycommunity. And while there, you'll find easy ways to navigate and find the resources and learning content relevant to our security products and their communities. A good start would be browsing our bite-sized product videos, ninja trainings, recordings of past webinars, GitHub communities, and more. We love to hear your feedback on how we can improve these webinars. Please take a minute submitting your webinar feedback at aka.ms/security webinar feedback. Thank you and see you next time. Goodbye.